And today's speaker is Andrey Pilipenko with the talk Limit Series for General One-Dimensional Diffusions. Please. Andrey,
do you see my screen?
Yes.
Okay. One moment. This is my joint work with Gilles Wilmart from the University of Geneva. And today I will speak about the following general problem. Assume that we have a sequence of one-dimensional diffusions, so continuous and strong Markov processes, and the aim is to find general equations that ensure convergence of diffusions in distribution. Consider a few simple examples. The first example is the following. Assume that Xn satisfy the following stochastic differential equation where an and sigma n are bounded and continuous functions and sigma n is non-degenerate. Then it's well known that there exists a unique weak solution to this stochastic differential equation. And if we have convergence of initial conditions, then initial condition and pointwise convergence of coefficients plus the uniform boundedness, then we have convergence of processes in distribution.
I have a question.
Yes,
already. Do we assume that sigma 0 is bounded away from 0 here?
No.
But can
you see, we have uniqueness until Xn exits from any compact, because in any fixed compact, sigma n is separated from 0. If sigma n is continuous and is not 0. And, and if you have this, then probability that you exit a compact, a large compact during the fixed amount of time is small. So you can...
Your example covers the case where the sigma is just sigma 0 is 0 in one particular point?
No, sigma 0 also is not 0.
Oh.
So all of them are this. So supreme over all n and...
I mean infinitum. Because if sigma 0 at some point is 0, we lose, generally speaking,
where a, n, and sigma n are bounded continuous function for all n.
I see. Now I see. Thank you.
And maybe 0. And the proof of this result is very simple. We have weak relative compactness, and then it is not complicated to show that any limit point satisfies equation with
I see.
a coefficients a0 and sigma 0, and if a0 and sigma 0 are such that we have uniqueness, then we have uniqueness of a limit point, and that's all.
And the convergence in the space of continuous functions?
Yes, I consider convergence in the space C0 infinity of continuous functions with topology of the uniform convergence on compact sets.
Thank you.
And well, consider the next example. Assume that x epsilon satisfies the following stochastic differential equation. And let us assume that x epsilon at 0 starts from the positive half line. And we assume that this a epsilon is non-negative. It converges to 0 everywhere for positive x's, but in the neighborhood of 0, a epsilon is very, very large. So it's sufficiently large. So the drift pushes away from 0 if x is in the neighborhood of 0 or below 0. Then it can be shown that, okay, under some conditions, it can be shown that the sequence x epsilon converges to a reflected Brownian motion. Examples of a epsilon may be as follows. For example, okay, this is x, this is a epsilon of x, 0 for positive x's, and linear function, excuse me, for negative x's. And if epsilon goes to infinity, then the drift converges to plus infinity, and it's known that the limits are this. Sometimes this method is called penalization method. Or, for example, if a epsilon x is like this, like a epsilon over x, epsilon divided by x squared for positive x's, it can be shown that x epsilon cannot hit 0, and again, in a limit, it gives you reflected Brownian motion. Consider another example and assume that a epsilon is a smooth function with compact support. And we assume that a epsilon, in some sense, converges to a delta function. So a is like this, and a epsilon has this form. It was shown by Mykola Ivanovich Pilipenko that the limit of x epsilon is so-called skew Brownian motion with certain parameter. And observe that this drift in the neighborhood of 0 is very singular. So it is unbounded. It's really converges to a delta function. And well, you may define skew Brownian motion as a solution to the stochastic differential equation with a local time where gamma is this coefficient. And it's interesting fact that, okay, let us discuss this result a little bit. So what is the local time of the process? Oh, excuse me, I have to write it like L0 of t. It's a limit as epsilon goes to 0. So today I will consider mostly symmetric local time. We count the time that the process spends in a neighborhood of 0 in the interval minus epsilon epsilon. Then divide by the length of this interval minus epsilon epsilon, and then pass to a limit. And it's known that there is a unique solution to this stochastic differential equation for every gamma less than or equal to 1. By the way, if gamma is 1, then the process is reflected Brownian motion, reflected up. And if gamma is -1, then it's Brownian motion that reflects down. And if gamma is 0, then it's just usual Brownian motion. You see we can say that this function, so it's like integral from 0 to t of a function f epsilon of x epsilon ds, where this function f epsilon is indicator divided by 2 epsilon, divided by length of this interval. This function converges to a delta function in some sense, and this equation formally can be written as this: del is equal to dwt plus gamma times Dirac's delta function of the process dt. And the unusual fact is this: coefficients converges to alpha times Dirac delta function, but in a limit we have equation with parameter gamma, which is hyperbolic tangent of alpha times Dirac delta functions dt. So we have very unusual effect and certain non-linearity. So the limit process depends on approximation in certain nonlinear sense. Sometimes zero is called a membrane for a skew Brownian motion, and a skew Brownian motion so let me let us discuss this picture a little bit more. So the local time increases only when the process X hits 0. And if X is not 0, then increments of X are the same as increments for Brownian motion. So this process behaves like a Brownian motion until it hits 0. So if it is positive or if it is negative, its increments coincide with increments of Brownian motion. However, when the process hits 0, there is effect of 0. We add something continuous. Well, if gamma is positive, then this process pushes skew Brownian motion up in certain sense. And the effect of 0 disappears if the process X is strictly greater than 0 or strictly less than 0. Moreover, this process, this skew Brownian motion, can be also constructed in another way. You may start from reflected Brownian motion. You have excursion. So excursion is a path between two zeros, and then toss a coin, and with probability P, you leave the process as it is and flip with probability Q, which is 1 minus P. And P and Q are such that P minus Q is this parameter gamma, this parameter. And now consider another example that was considered by Sergei Makhno. Assume that there are a lot of membranes located in points sorry, there is a typo, epsilon k, epsilon n1, epsilon n2, epsilon n3, and so on, epsilon nm. So there are membranes here, so there are local times. The process behaves as a Brownian motion everywhere outside of m points. Assume also that all these numbers converge to 0 as n tends to infinity for every fixed k. Then it can be shown then when all these membranes compress into one membrane, then a limit of this process will be again a skew Brownian motion with certain parameter gamma, and I will write the explicit value of this gamma a little bit later. Also consider the following assumption. So we know that if the drift converges to delta function or delta function multiplied by certain constant, then in a limit we get skew Brownian motion. If the drift is very large in a neighborhood of 0, for example, it's finite function such that 0 here, 0 here, and grows in some sense greater than delta function, then in a limit we obtain reflected Brownian motion. It appears that there is some intermediate model if this drift AN has the following form. So it is positive for positive x in a neighborhood of 0. It's negative for negative. It's finite function, and we assume if a epsilon, there is some balance. If a epsilon is quite large, larger than delta function, but not too large, then in the limit you may obtain the following interesting process that appeared independently in my joint paper with Mandekar and we in a paper by Antoine Léger. We called it Brownian motion with a hard membrane. Antoine Léger called a process snapping out Brownian motion. And the process behaves like this. So at first, well, for example, assume that you start from the positive side. The process behaves like a reflected Brownian motion, and it accumulates its local time at 0. And when this local time hits reaches some critical level, so some random variable with exponential distribution, then the process changes orientation and behaves like a Brownian motion reflected down. And again, it counts its local time, and when it hits certain critical level, again, another exponentially distributed random variable that is independent of all the past, it change orientation and again and again. And we obtained this process by this approximation. Antoine Léger, he considered two membranes located in points plus epsilon and minus epsilon. And this parameter gamma plus, like permeability parameter of membrane, was close to 1. So the probability P epsilon in this point behaves like this, like some parameter times it's so probability to go right is close to 1. Is close to 1, and probability to go left is proportional to epsilon. And at this point, probability to go left when you hit this point again is close to 1, and probability to go right is close to epsilon with certain parameter is proportional to epsilon. Well, and it can be shown that in this model and in this model, it's possible to obtain this so-called snapping out Brownian motion. And today I would like to formulate very general conditions on coefficients that cover all these examples. Well, and the next result is due to Friedlin and Wenzel. And we will discuss this result later. And I will show you the proof of their result and certain generalization. And it seems to me that my proof is much easier than theirs. Okay, so it is well known that every one-dimensional diffusion, that the generator of one-dimensional diffusion has the following form: is a second-order differential operator. This function Sn is called scale function. So it's continuous, strictly increasing function. And Mn is called a speed measure. So we will discuss exact formulation a little bit later. Wenzel and Friedlin showed that if Sn scales converge to a scale of a limit process and speed measures converge in some sense to a speed measure of the limit process, then we have convergence of processes. Well, and one small remark. I always assume that initial conditions of diffusions converge in distribution. So I will not say this in all my theorems. The proof by Friedlin and Wenzel was as follows. It is known that convergence of resolvents of processes is equivalent to convergence of processes in distribution. Well, if initial conditions converge. They calculated resolvents and proved the limit result for resolvent, and they deduce convergence in distribution of one-dimensional diffusions. When I say that the generator has this form, well, to be honest, I need to be very careful because I need to say what is the domain of the generator, and if diffusion, say for example, is reflected Brownian motion or reflected diffusion, then what are the boundary condition at the point where the process reflects? Wenzel and Friedlin considered a spatial case where diffusion x0 was considered on a certain open interval that may be infinite, and the assumption was such that this diffusion can hit every point of this interval with positive probability, but cannot hit the boundaries. However, assumptions on xn were not as strong as assumption on x0. In their theorem, and also in my theorem, the domain of xn may be larger than this interval for x0. Okay. So today I will consider diffusions, and a diffusion is a strong Markov process with values in a certain interval that may be bounded or unbounded, and boundary points may be included, included. It does not really matter. Set. If I is a certain set, then all the points are reachable with positive probability from inside. So if you have a point x inside the interval, so inside the inner part of this interval, then with positive probability you can hit any point y, this point, or maybe this point. Well, if this point is not included, then this point cannot be hit with probability 1. So I assume that x of t belongs to I with probability 1. So if point is not included, then you can't hit this. And one small remark, if you start from the boundary point, then theoretically you may stay here forever. For example, this point may be a trap. You walk here, you diffuse, and when you hit this point, you can stick here forever. Well, it's known that there are two functions strictly increasing continuous function s on I, and m that is locally finite on the inner part of the interval, such that measure of every finite subinterval is positive and less than infinity. Well, measure m of the boundary point may be infinite. And it's known that the generator has this form, and on the next slide I will show you what does it really mean. So what does it mean, differentiation with respect to measure? And I will explain what is the domain. So we may introduce the right derivative with respect to s, the left derivative with respect to s in a natural way. And this operator is just the following limit. And domain of the generator is a set of uniformly continuous functions on I, bounded and uniformly continuous functions on I. Such that if I is infinite, then there are limits at the infinity, such that derivative with respect to m, derivative with respect to s from the right is equal to derivative from the same operator from the left, and that this operator, this function must be continuous, bounded, and have limits at the boundary points. Plus maybe some boundary condition at the end of the interval. So if the end of the interval is included and is finite point, then you have to add a boundary condition. Well, it appears that if measure m of a point is 0, for example, if m is continuous distribution, then for all points, if f belongs to the domain, then derivative from the right is equal to derivative from the left. And if x1 and x2 are not atoms of measure m, then you have this equality. And formally, if you differentiate with respect to m, left-hand side and right-hand side, you obtain this function. Well, it is also known that if m has the atom, then derivative from the right and derivative from the left satisfy this property. Satisfy this property where A is a generator. Okay, and boundary conditions. If say alpha is the left end of the interval I, is like this: measure m at the point alpha multiplied by generator, and A of f is like limit from the right of these expressions. It must exist. Is equal to the derivative of f from the right. Well, and if you include the right point, you have a similar expression, but you have to consider derivative from the left and atom at this point and generator at this point. Well, if m has a continuous distribution, then it's like Neumann boundary condition, derivative is equal to 0. Well, derivative with respect to scale is 0. If m of the endpoint is infinity, then the boundary condition is this: generator is 0. Okay, so this is analytic description of a diffusion. So it can be proved that if you have a measure m that satisfies certain properties and a scale function s, which is continuous strictly increasing function, then plus boundary conditions, then you can construct a strong Markov, moreover, failure process on I. There is another construction due to Ito and McKean, who constructed a general diffusion like a space and time transformation of a Brownian motion. And the formula is like this. This is inverse function. So S is a scale. It's continuous, strictly increasing. So inverse function exists. L is the following integral functional, and excuse me, and here L is a local time of a Brownian motion. This is a generalized inverse function, and it was proved by Ito and McKean that x of t defined by this formula is really a diffusion whose generator is 1/2 times derivative with respect to m, derivative with respect to s, with respect to scale. Well, if I is R, then we know that m, that measure m of every every interval is strictly positive. Then it can be shown that a of is continuous and strictly increasing process. Then its generalized inverse is just usual inverse. Well, however, if I is 0 infinity, for example, we have reflected process, then okay, we will see this. Then we have to integrate with respect to we have to integrate over this interval 0 infinity, and a of t is just non-decreasing process, non-decreasing continuous. Let me present the first my first result. Assume that we have a sequence of regular diffusions on IN, where IN is interval alpha n, beta n, and you may include these points or exclude these points. And we assume that scale functions converge to a scale function of certain process x0 pointwise. We assume that in some sense this xn have so these in are larger in some sense than I0. This means that alpha 0, beta 0. So theoretically, this alpha n, its limit may be strictly less than alpha 0, and limit of beta n may be strictly greater than beta 0, but okay, it may be alpha 0 and beta 0 also. We have convergence of scales only on this interval alpha 0, beta 0, the interval where the limit diffusion lives. And we also assume convergence of measures. Sometimes this convergence is called VAG convergence of measures on VAG convergence on this interval alpha 0, beta 0. So this means that if you consider every continuous function whose support is a subset of alpha 0, beta 0, then you have convergence of integrals. Now we construct diffusions by a formula by Ito and McKean. And if x0 is a regular diffusion on an open interval. So with probability 1, you do not hit alpha 0 and beta 0. And if you have convergence of initial conditions, then you have almost sure convergence of diffusions. And now you may think like this. Okay, assume that you have diffusions Xn with generators these such that their initial conditions converge to x0 and Mn converges to M in some sense, and scale functions also converge to S0 in some sense. Do we have convergence in distribution of Xn to x0? The answer is yes. We can construct a probability space and some representation of this diffusion on a common probability space such that you can construct copies of these diffusions on some probability space such that initial conditions converge, and this diffusion converge almost surely. So if you have almost sure convergence for copies, then you have convergence of diffusion of originals. And the proof, okay, assume for a while that that all INs are real lines. Let me explain you then. In this case, the theorem is obvious. Indeed, you have this representation. You have pointwise convergence of continuous and strictly increasing functions. If you have pointwise convergence of continuous increasing functions, then you have uniform convergence. Then it's known that if you have locally uniform convergence of continuous and strictly increasing functions, then you have locally uniform convergence of inverses. So you have convergence of these, you have locally uniform convergence of inverses. And by the way, we know that the local time of the Brownian motion is a function which is continuous in both arguments. And we have locally uniform convergence of these to S0 of y minus S0 of x0. And hence you have locally uniform convergence of these processes to L by 0 t with this. And you have VAG convergence of measures Mn. And you may observe that actually the local time is 0 if Brownian motion does not hit a point up to a time t. So it's a problem from analysis it's not complicated problem from analysis to prove that the integrals also converge to integral of the limit. Well, if I0 is not a real line and alpha n are strictly less than alpha 0, the proof is similar. And this is result from mathematical analysis. And that's all. So you prove that you have convergence really for almost all points, and almost all means the points where the local time is continuous in both of arguments, and that's all. Now let me consider examples. And let me just before we discuss examples, let me explain some probability meaning of scale function and speed measure. The meaning of scale function is this. If you start from a point x, and there are 2 points y2 and y1 such that x is in between, then probability that the process hits y1 before y2 is proportional to the scale. It's equal like distance between y2 and y1. Okay, distance in this scale. And numerator is distance between, okay, this is an error. It should be s of y2 minus s of x. So like this distance opposite this distance. And well, the speed measure is related with the time spent in interval y1, y2 up to the exit from the interval by the following formula. One delicate moment. So I cheated a little bit because I said that if you have a locally finite measure and locally finite measure m on certain interval and strictly increasing function m s, then you can construct a diffusion on I. The delicate thing is, should we include or exclude boundary points? There are necessary and sufficient conditions when we must include boundary points or exclude them. For example, if the scale is, okay, if S of alpha is finite, so, and if the measure of a neighborhood of alpha is included, is finite, then you must include alpha into I. And example, it's like a Brownian motion, reflected Brownian motion with reflection at alpha. Then the process can hit the point and exit from this point, and then hit again and exit again. Sometimes this point is called regularly bound. Another case is, for example, for example, if the scale is unbounded in the neighborhood of alpha, then the process never hit alpha. Never. And imagine like the distance to the point alpha in the scale is large, is like infinity. Then you need infinite amount of time to reach this point. Okay, but there are another possibilities when you can hit point and stuck here and cannot exit, or if you if the limit of xt as t tends to infinity, maybe alpha, but you never hit it, like for geometric Brownian motion and so on and so forth. And now examples. At first example of scales and speed measures. For usual Brownian motion, S of x is x, m dx is dx, so density of m is just Lebesgue measure. So m is Lebesgue measure. However, if you multiply s by a certain constant and divide m by the same constant, you obtain the same process. Again, a Brownian motion. Reflected Brownian motion, the scale is x, speed measure x, again linear, is a Lebesgue measure on 0, infinity. And that's all. If you have if X is a solution to a stochastic differential equation with nice coefficients.
Andrey,
Yes?
excuse me. When you said about reflected Brownian motion, maybe you must say something about boundary condition at 0.
Yes. Okay, boundary conditions are this. So m of 0, so measure m of 0 is 0. The boundary conditions are like this: m of 0 times generator, and generator is now a second derivative, is equal to ds of f at 0. Now, ds, derivative with respect to s, is just usual derivative, so f prime at 0, derivative at 0 from the right, is equal to, this is 0, this is 0. So this is just Neumann boundary conditions.
Okay.
And the generator is 1/2 times second derivative. Derivative with respect to dx, and again with respect to dx. Well, for stochastic differential equations on a real line with nice coefficients, S and S is any functions whose derivative has this form, where derivative of phi is this function, and the M is absolutely continuous measure where density has this form. So everything can be written explicitly. My next example is a skew Brownian motion that can be defined, for example, by a stochastic differential equation. And its scale function has this form. So it's piecewise linear function. And the speed measure is proportional to Lebesgue measure with coefficients p and q, like 1 plus gamma over 2, 1 minus gamma over 2. So gamma is p minus q, where p is 1 minus q, or q is 1 minus p. Well, you may multiply s by any parameter alpha, then you have to divide m by this parameter alpha. Alpha is positive number. Boundary conditions. So boundary, okay, not boundary condition. The generator is 1/2 times the second derivative for all points except of the 0. Second derivative at 0 must have a limit. So second derivative, the limit of the second derivative from the right must be equal the limit of the second derivative from the left. Well, the function must be continuous, and the first derivative. So let me recall you that derivative from the right at 0 should be equal derivative from the left. But we calculate derivative with respect to s, and this means that p times derivative from the right, well, usual derivative, because now s is proportional to x, is equal to q times derivative from the left. Okay. And now the result. Consider the following stochastic differential equation, Well, it behaves like a skew Brownian motion, but with many membranes. This means that the scale function is piecewise linear. These points are epsilon and k's, and ratio of slopes are equal to pk over qk, where gamma k is pk minus qk. And the speed measure is proportional to Lebesgue measure, and if the slope here or there is equal to certain parameter, say beta, then the density of measure m on this interval is equal to 1 over beta. And now the result. So if you write explicitly scales for these functions and speed measures of these functions, and if we assume that epsilon and k converge to 0, so all these positions of membranes converges to 0, then the limit of scale functions will be a piecewise linear function, and the point where with one point where you have a jump of derivative, and this point is 0. And if you calculate the jump of derivative, you'll have that the corresponding ratio of slope for positive axis and negative axis is equal to ratio of this product. And you know how to calculate speed measures. Okay, it's again Lebesgue measure, maybe it's proportional to Lebesgue measure. And if you calculate the density, you'll see that the limiting measure m0 is a measure for a speed measure for skew Brownian motion with parameters p and q given here. And by the way, if these parameters gamma k are equal to hyperbolic tangents of alpha k, then the parameter of the limiting skew Brownian motion is hyperbolic tangents of a sum, and we have a very beautiful formula. Another examples. Assume that you have two membranes located in minus epsilon and epsilon, and assume that these p plus and q minus, so probability that you go right is small, and the probability that you go left here, q minus epsilon, is also small and proportional to a certain function lambda of epsilon that converges to 0, but not as fast as epsilon, then it appears that the limiting process is again a skew Brownian motion with certain parameter. And the proof is simple. You just write explicitly scales and speed measures which are piecewise linear function, and then pass to a limit. Another question, and what happens if almost same situation, but assume that these probabilities are proportional to epsilon. So you reflect to the right here and to the left here with probability that are proportional to epsilon, then it can be shown that the limiting process is a sticky skew Brownian motion. So what does it mean? You take a skew Brownian motion with this parameter, and then you make the transformation of time. Oh, I have to write t here. So you calculate the local time of this skew Brownian motion, and this is continuous additive functional. This function is strictly increasing. You consider this inverse function and a composition of these two. It can be shown that with probability 1, this process spends positive time at 0. Okay, there are also results when you may get reflected processes, or the processes where a boundary point is a trap, and the results looks like this. You have convergence of scales, you have vague convergence of speed measures, plus some behavior in the neighborhood of the boundary. If the boundary is included, then you have convergence of in the distribution of diffusions. And the proof is mathematical analysis. You construct diffusions using the same Brownian motion on the same probability space. You use representation by Ito and McKean and use certain theorems of mathematical analysis and then pass to a limit. That's all. Thank you for your attention.
Thank you very much for interesting talk. Maybe someone have questions or comments, please.
Well, I have a question about this, your new equations, like snapping out Brownian motion. Is it interesting to construct a flow of such Brownian motions?
For snapping out Brownian motion, the flow should be okay. It will be very degenerate. So at the beginning, you have okay. I don't know, will it be degenerate or not? Because there is one problem. Assume that you start from a certain point and you have reflected diffusion. Well, if you start here, you are below. You are below this point, and if this process does not change its orientation, then they must coalesce and move together. But what is the exponential time for this process and for this? They may be same or different or correlated, be dependent, independent. So it depends. You may consider the following approximation. Okay, I didn't formulate. I can obtain the snapping out Brownian motion as a limit of diffusions.
Yes.
And I don't know. Yes, it would be interesting. What is the limit of flows? Because for pre-limit processes, you know what is the flow. You know what is the flow. Particles do not coalesce. Particles do not coalesce. They never meet together. So you have some monotonicity, and well, probably it's possible to to say that a limit of flows exists in some sense. But
maybe it will not be a flow of maps.
But you have to be very careful, because for snapping out Brownian motion, 0 is a very special point. Actually,
okay.
It's better to consider not a real line, but the union of to consider like 0 plus and 0 minus.
The 0, yes.
Yes, and the state space for snapping out Brownian motion is this. On this set, it is strong Markov process. And you start with flows here, but you obtain the flow here. I think it is possible, but I don't know the answer.
Okay, thank you.
Okay, thank you. Other questions, please?
I have the following question. Can we add some stopping times into this picture, at least stopping times for reaching levels?
Yes, sure.
Yes.
Absolutely. You're absolutely right. Result is the following. Assume that certain intervals is included. Okay, assume that B is included into is compactly included into I0. So and assume that you start from this interval AB. Then, if processes xn converge to x and the process xn have representation as speed measure converge, scale functions converge here. Then it can be proved that the processes stopped when it exits the interval also converge in distribution. So xn dot sigma n, sigma n a minimum sigma n b, comma sigma n a sigma n b. So this triple, the stopped process, and also this converges in distribution x0 and the limiting heating times. By the way, if you consider xn as a functions of the same Brownian motion and use Eaton-McKean construction, you will have almost sure convergence.
Interesting.
And this is almost trivial. This is actually, at first I proved this result. And stopping times, so heating times are not continuous.
Yes.
But if, and now let's consider just a deterministic situation. Let's assume that function f0, x is f0 of t, and the level a is the following. Well, assume that this heating time is finite, and then in any neighborhood of this heating time, there are points when you are above 0 and above this level, and you are below this level. Yes. Then, if functions fn converge locally uniformly to f0, then you have convergence of heating times. And diffusions, they are functions of a Brownian motion, and Brownian motion has this property. So we don't have a problem with these heating times. They are continuous with probability 1.
Yes, but it's very general results to obtain.
Yes.
Very interesting. Thank you very much.
Thanks a lot, Andrei, for interesting talk. About this snap out, can it be considered in higher dimensions, say 2-dimension, and also can you add drifts? And if yes, what is the reference?
Okay, it can be done, but there is no reference. Okay, let me explain. Okay, it's the result can be guessed from one-dimensional situation. So you can consider, for example, hyperplane. Okay, a line, for example. You have a diffusion. The xn of t is well, some sigma xn of t dwt. Well, sigma is nice, so non-degenerate, hyperelliptic, separated from, yes, so nice metrics, and regular drift dt plus some perturbation in the small neighborhood of this, plus bn xn of t dt. So I believe that it's possible to write more or less reasonable function on this bn. So bn should be like this. It should reflect. So it's like potential pushing the process strongly to the right if you are here, and to the left when you are here. And it should be some balance, such that it's very hard to penetrate. So usually when you enter this small neighborhood, then the drift bn pushes it's to the right, but sometimes it may hit this hyperplane, and if you are here, then it's 50-50, go left and right, and if you go left, then the drift here is strong, it pushes you over there, and you try, and you make like successes and failures, and sometimes you can penetrate. So probability to penetrate this, so if this distance is like 1/n, so it's like successes and failures. So you hit, for example, this, then you have decision: do you penetrate or you return back? And the probability of penetrate should be small, but not very small, such that if you have a lot of trials, then so like probability 1/n and trials, and then you have certain balance that then you can pass through the membrane. It is not written. No, I have not seen this. I have not seen this result in whole generality. Well, only if you have two coordinates, and if one coordinate is independent of other, and if you solve equation for x and y separately, then certainly you may find, you may prove that the limit is multi-dimensional snapping out, but this will be one-dimensional result. Yes, so this is the answer. So I think it is possible, but it is not written. And boundary conditions for this snapping out, it's called Newton law of cooling. In one-dimensional case.
Yes, that's I understand. Yes.
Yes. So derivative is proportional to difference of temperatures.
Yeah, that's clear from physics.
Okay. Other questions, please? Andrey, let me ask you about the following. When you consider the multiple set of membranes, which collapses to one at the point zero, what happened with the local times of the pre-limiting diffusions? They goes to zero or what? Or can you say something?
No.
No.
No. So you have equation with many. So
Exactly. Yeah. You consider this when they approach zero, these membranes. I think. Yeah, like this one. Yeah.
no. So they are summed in some sense. You sum these local times in some sense.
Okay.
But in strange way, in strange way, these hyperbolic tangents.
I see. But my question is related to the Engelbert and Chorny book about the construction of one-dimensional diffusion using this local times and using the random change of the time in the Brownian motion. Yeah?
Yes, so I use this technique. So I consider. So let me show. So I consider local times. I consider if mn dy is a function, so if it has a density df of y dy, actually this integral is integral of local time with this, and then you change this.
So it is like
the name of occupation time formula. Yes. So in some sense, an is integral functional of a Brownian motion, and you actually you use the local time of the same Brownian motion, and you have convergence for almost all omega. And you just apply analysis results. So you may look at local times of those processes. Oh, let me tell you. Yeah, it is a question. Okay, this is a question. What is okay? What is the local time of this process X? The answer is the local time of process X at a point Y. The local time of the process X at the point Y at the instant of time T. Oh, the instance of time T is equal to the local time of a Brownian motion at the time this and at the point S of Y. You may ask me, and okay, what is the definition of a local time? Because there is symmetric, non-symmetric, and so on, local time. If Y is inner point of I, of this interval I, then LTY of X is limit. Maybe I wrote. One moment, I have a slide. This is a formula, and this, and you may consider symmetric. It's also the case. So you have to calculate the time. You have to calculate the time spent in interval and divide by measure m of this interval.
Mhm.
And you have this occupation times formula, but you integrate with respect to measure m dy.
Mhm.
If a point y is a boundary point, then you have to consider, for example, y is left point. Then this is the definition of local time. If it is right, then you use this formula. So the same as for Brownian motion. So similar approach.
I see. And coming back to this multi-membran case, it looks like there is some interaction between these membranes through the local times, yeah?
Yes, there is some interaction. Yes.
Yes, we take this integral multiple, like integral local time for this. And okay. Thank you very much again for interesting talk. For today, we finish our job. And Katerina, do you know who will be next speaker?
The next speaker will be Gennady Levrotsky.
Okay, good. So see you next week. For today, that's all. Bye.
Goodbye.
Thank you. Bye.
Goodbye.